My colleague Mads and I are working with darts as the two primary persons in MSCi. My name is Rasmus Bøge Hansen. I am a chemist specialized in especially mass spectrometry and later on in chromatography. So now we will talk about something where we don't use chromatography at all. I've been working for MSCi for quite some years now, and today I will talk about food fraud analysis, food authenticity, and raw materials in general. So I will try to share my presentation here. So, for fast food fraud analysis of raw materials and food using data combined with statistical models. Well, that's a rather long title. It seems very long and complex, but let's just say that things are not necessarily as complex as the title seems. But I will start to make a very short introduction about who are we, who are IonSense. We'll talk shortly about what is the DART, about its modules and sample preparation, and about the Analyzer Pro software. Then I have an example, an application sample of oil analysis, edible oils, and the second example about milk analysis, which are the two main parts. So if you came for the application work, don't worry, those two will fill most of it. Lastly, we have the possibility of answering questions. So if, as Mads mentioned, just ask any questions alongside the presentation and we will discuss them in the end. So MSCi has been existing for 24 years now. We started as a company providing training. Today we offer much more than that. We also do instrument sales, service support, application development, method validation, and lots of things in the field of mass spectrometry, chromatography, and analytical chemistry in general. Those are our main focuses. And we are the Nordic and European distributor of the darts, the ambient ion source that comes from IonSense. So that leads us to IonSense, which is based in Saugus outside of Boston in the US. They are a leading manufacturer of open air ionization or ambient ionization. So basically they manufacture the dart, which does ambient ionization. This is a dart, and while it may look a little bit complex, it's basically just an ion source for mass spectrometers. It's easily mounted on top of an existing mass spectrometer for LC-MS. You just decouple the LC and add the dart instead. So the dart is direct analysis in real time, and that means that we ionize our samples, introduce them directly into the mass spectrometer, and then we see our mass spectra in real time. We don't have to wait for the chromatography to end. We just do the analysis directly without any kind of separation. And for all of those that come from the world of chromatography, which I myself did, the first question is how to separate all of the molecules, how to separate everything that is normally separated by chromatography. And the thing is, you don't. You look at the data instead and do it by data analysis. And this is one of the strengths of DART, that it works fast, you work with it in real time. So DART is basically atmosphere ion chemistry. And though some of you may have worked with ionization chemistry in open air, and some may not. A lot of you may have worked with it in vacuum, but it's different than vacuum, because in vacuum the ions are alone, but in open air they're not alone. They have lots of air molecules, water, and whatever chemicals may be in the open air around the ionization. And while that sounds pretty complex, it actually ends up with some relatively simple ionization mechanisms. So by ionizing in open air, you get a lot of direct ionization, that is the M plus ion. You get a lot of M plus 1, that is protonated molecules. With negative ionization, you can also get a lot of direct ionization, or you can get proton abstraction. The important thing here to remember is that the ionization mechanism for certain molecules are the same all the time, unless the atmospheric conditions change by, for example, introducing some chemical that wasn't there normally. So you get a lot of ions, but one type of molecule always gives you the same kind of ions under the same circumstances. So the analytical prerequisites should be the same all the time. I will not go into details with all of these kinds of reactions. I just want to show you that this is ion chemistry in open air. We have reactions with water and so on. So when you do sample introduction into the DART, how do you actually do that? And one of the points of the DART is that you can do it very fast. You can just take your object, sample, leaf, whatever, and you can just place it in front of the DART source, and you can analyze everything that's on the surface. You can analyze droplets, you can analyze dry droplets on small grids, and again, I will not go into details with the different modules displayed here. You can just see that there are some various ways of introducing the sample. We also have some amount of possibility of doing automation, so that you run several samples at a time. You can run up to 10 tablets, medical tablets, or you could also do it with grain, nuts, or whatever small solid objects. You have, again, grids you can place it on, and automate running 12 samples, 96 samples, even 384 samples in one run. And you have a 24-pit liquid sampler, which is displayed here. And the reason why we display this particular one is that we have an example using that later in the presentation. So for this particular module, please pay attention to how it looks, and we'll talk a little bit about it later on. So you can analyze inside. You can do, like you could do with the biscuit here. You can analyze several replicates of the same sample, like you do with honey, or even fix into small microchips plates or deep well plates. So you just dip the sampler into it, and you just analyze those 24 wells in one run. Very shortly, we have the 384 sample module, which is called the high throughput sampling. And this is basically a grid where you place 384 samples. You need to do that by pipetting, and I don't know about your pipetting skills, but mine are not very accurate. If you make a robot do it, it's much more reproducible, and you get much more reproducible results. So, and also pipetting 384 samples is quite a workload to put on a person. So for these kinds of systems, we really advise to have some kind of robot, like the Hamilton robots, lab-check mosquito, with different possibilities like the Gerstel MPS, which we sell but haven't used much for this. So, what does it look like when we get these kinds of data from 384 samples? So we have an example here, and you can see that this is more or less like a chromatogram. If you look at it like a chromatographer would do, like I did in the beginning, we call it a chromogram. But each of these pins or peaks, if you would like, is one sample. And you can see they are spaced very tightly, and you have basically loads and loads of data. This also means that we must have some kind of way of processing these. We usually use the Analyzer Pro, which is, I wouldn't say it's born for the Dart because you can use it for a lot of other things as well, but it's ideal for the Dart because it works with every kind of mass spectrometer, at least what we know of, and if it doesn't, it will get to work with those kind of data. So the Analyzer Pro looks through this file for 384 samples, and you can see that the data here are very nicely spaced and easy to detect. And the Analyzer Pro will split up the data file in 384 different data files, which you can work with individually, or you can do statistical analysis on them. In this case, we've used pulsing, which gives you a very more close, a very more distinct separation of the peaks. The classic way of doing Dart is to not doing pulsing, and you'll have some amount of baseline between the peaks. That makes it much more easy to work with, and also in many cases gives you better sensitivity. So this software is an example of one you can use for doing the statistical analysis. That is one of the large strengths of the Dart. So until now, you may have the impression that I'm doing a sales speech. That's actually not what I'm supposed to do. It's not either what I want to do. I want to show you some real-world examples. You may remember this 24-pin module that I mentioned earlier and showed you earlier. And one of the strengths with this one is that you can analyze the inside of a semi-solid sample, like, for example, a burger. So you basically take the pins, you just push it into the burger, you withdraw it, and you sample it. And then you have the inside of the burger sampled and ready to be analyzed. This is what we have done here. The mass spectra here are, of course, not from all 24 pins, but just one of them. What we want to see is what is the difference between a plant-based burger and a meat-based burger. And the manufacturers try to make them taste as much alike as possible, but is there a difference? When we look at the mass spectra here, you will see that the Impossible Whopper, which is the plant-based one, is very distinct from the meat-based one. You can see there are several peaks that are present in one of them, which is not present in the other one, and the other way around. So they are very easy to see the difference between. When we have enough data, that is, we have to do at least 3 replicates of each sample, then we can do a statistical analysis. And in this case, we have done a PCA, primary component analysis plot of those 2 different burgers. And you can see in the diagram on the left, the PCA plot, that the blue one is the plant-based one, and the green one is the meat-based one. And you can very easily see that it's very, very distinct grouping of the samples. And it's very easy to see the difference between the plant-based burger and the meat-based burger. So this is one way to, one example of how to differentiate different products based on the statistical analysis of a data set that is statistically large enough. Another way of using the Analyzer Pro is to do plate mapping or heat mapping. If you look for a specific kind of adulteration component or additive, then you can specify the limit for the detection limit or the lower limit for how much is allowed of this additive. And you will see that if the additive is present in the dark data, you get some kind of warning in the heat mapping. And in this case, it's black cohosh, which is naturally occurring plant that has some extract that is used as during menopause and to relieve pain. I believe it's a natural medicine, you can say. But in this case, you can see that it has been adulterated with sildenafil, which is an active component in Viagra. And if you want to detect these kinds of frauds by introducing possible illegal substance or something that's not supposed to be there, but sometimes is anyway, then it's a way of doing this. And you can see in the mass spectra in the bottom that the sildenafil is occurring in the adulterated sample, but is not present in the unadulterated. And when you run enough samples, like the 96 samples we've run here, you will see that some of them is clearly coming out as positive. That means that you are over the limits of the limit that we have set in the software. So that's a different way of detecting food fraud, by looking for additives or something that's not supposed to be in the sample. So I'll show you some examples here of some products that are usually considered as important products. They might be more expensive than standard products or similar than that. So we will look at some examples for olive oil, we'll look at some examples for milk, and we'll look at some addition detection. So olive oil, when you buy olive oil in the store, you will have some that is labeled extra virgin, some is labeled virgin, and some doesn't have a label. So the extra virgin is when you press the olives, the first fraction of oil is the extra virgin. And due to mechanisms, I don't know how it works, that is the best health-wise fraction of the olive oil. It contains a lot of the unsaturated fatty acids, while the later fractions contain less of these and more of the saturated samples, fatty acids. And here we have run some samples with extra virgin olive oil. We compare it also to hazelnut oil and to virgin olive oil, which is the second fraction, and to standard olive oil, which is all the rest. And looking at these spectra, my first thought is that they're the same. They seem to be almost identical. If you look closer, you'll see that especially in the low area around mass 200 to 300, or 350 actually, there are some small differences. And if you look even more closely, you will see a very few differences as well. But they basically look the same. And that is because olive oil is based on, it contains the same distribution of main components of fatty acids is the same in all fractions. It also compares very closely to hazelnut because they are all same class of plants. So the main components are possibly the same, but is there a difference? And if we look more closely at the low level, the lowest half level of the mass spectrum, we'll see that there is a very clear difference. So these are a lot of components that are present in different fractions of the olive oil, but we'll also see that there's a very large difference to hazelnut oil. So even though they look the same in the mass spectra, they are not the same. And this is one of the important things to keep in mind when doing fraud analysis, because you don't necessarily have to see for products that have been replaced with something different, but you may also need to look for something that has been adulterated by adding a small amount of a cheaper product. So if you want to look at olive oil, you will need to look for some of these markers in these mass spectra that are different between the different fractions. And that's not necessarily the large components, but the small ones. If we look at the polyphenol area in olive oil, we'll see a lot of different components occurring here. And these are, as it's mass spectrometry, all ionic in nature. And we'll see that some of them has occurred by water abstraction, that is mostly D-alcohols. And we'll also see that some of them has occurred been created by protonization, which is basically done by protonating it with the water in open air. We have included the example of sodium adduct ions. They don't occur in the darts, but some of you may come from the moldy world, and in the moldy world, the sodium adducts are very common. So we've mentioned it to remind you that it's actually very close technology to moldy, but it's not the same. We have none of those because there's no sodium ions in open air. So we see the other ones. What happens when the extra virgin olive oil gets old? And what we look for here is some of the components that are naturally occurring in large amounts in the extra virgin oil when it's new. And we can see, for example, the tyrosol and the hydroxytyrosol, they are present in freshly pressed olive oil. If we do aging of it, well, by let it stand for half a year, for a year, for 2 years, or something like that, or if we do the accelerated aging by putting at an elevated temperature in the open air, then we simulate aging, we'll see that the tyrosol gets much smaller when you let time pass and oxidation happens, but you also see that some degradation products, which are shown here, suddenly show up, which were not present in the original olive oil. So this way we can look for these degradation products to detect whether this is old or new. And You may remember how small this area was in intensity compared to the large components in the mass spectrum. And if tyrosol was one of the large peaks, then the degradation products here are pretty small. So they will not be seen when you just look at the overview of the mass spectrum, but they will be there anyway. And this is why we need to, again, remember that we are looking for the small differences, because the large components will be the same. If we look at some examples here, where we have the extra virgin oil, the olive oil, which is standard fraction, cheap fraction, but we also have the refined pumice olive oil. And this is when you have pressed all oil out of the olives, you have only the shells left. And if you press them one more time, you can get a little bit more oil out of it. But you'll also see that the oil you get out of the shells or the pumice is very different from the extra virgin olive oil, and you'll see that it contains completely different distribution of this polyphenol area of the mass spectrum. So again, you can now see the difference between different fractions of olive oil. You can see whether it's old or new, but you can also see whether it's from one fraction or another by looking at these markers. This means that we can look at all those markers that we have now established exist, and we can use them to set up a statistical model to detect whether we are looking at one or another kind of oil, whether it's old or new. And this is usually done by statistical analysis. You may remember me saying several times that we're looking for the small differences, the fingerprint areas. We're not looking for the large components, and that means it's very difficult for the human mind to see those kinds of differences. But if we look at statistical models, like for example the primary component analysis, it's very easy to see those differences. In some cases it may be different, be more difficult, but you can see, for an example here, that we have run samples of old olive oil from 2019 or earlier versus fresh. You can see October 2020, that already tells us this was done a couple of years ago. And you can very easily see that that they group very differently. And it's very easy to see within 95% confidence area that these are very easy to discern from each other. So by running enough reference samples, you can set up a statistical model. When you have this statistical model, you will have the possibility of running unknown samples, and you can very easily group these in one or the other area and determine whether this is old or new. Basically from the mass spectrum features we looked at before, but the statistical model is doing this for us, so it's more easy to see. The last thing I will talk about with oil is that different kinds of oil is very different. You can see fish oil contains a lot of EPA and DHA, the two last ones, while safflower oil contains a lot of oleic acid and linoleic acid. The flaxseed oil contains the same two things, but it also contains a lot of alpha-linolenic acid, which is not present in safflower oil. The point of this is that if you, for example, say that, well, fish oil is very expensive, if I dilute it with some kind of other oil, like the flaxseed oil, people will buy it and I will earn more money. So this is an adulteration example. But if you do that, you will very easily see in the statistical models that some fatty acids show up that shouldn't be in fish oil. And if you set up this statistical model by references of fish oil and run some references of flaxseed and safflower oil, you will very easily see some of the features of the oils that were not supposed to be there to show up. And you can easily detect whether a product is adulterated. I will talk a little bit about milk analysis. And this is based on this article. I've quite a lot of times said that we have done, but this is a lot of work done by other people. So thank you to those, of course. I just want you to know that we didn't do this. First of all, we have done the sample preparation, which is an extraction of the fatty acids or organic compounds in the milk with toluene, with methanol, and we have run the methanol extract in both positive and negative ion mode. And you will see that the mass spectra obtained by the extract is very different. And why is this? Well, between toluene and methanol, you'll see that there's a lot of different, because the solvents are very unlike each other, so they will have different extraction properties. But when you run the methanol extract in positive mode and negative mode, you will also see that there's a lot of difference in the mass spectra. And this tells us that it's not just a click and run after all. You need to consider how to do your sample prep, but also whether to use positive or negative ion mode with the darts. So we can look at some of the areas, and you can see that this is the high mass area, like 900 roughly. And if we look at these triglycerides, I believe it is, we'll see that we have the same present in the fresh oil and the oxidized oil. So this is cheese that is adulterated with rapeseed oil, which means that we are still talking about milk, just processed milk products. But when we talk about oil, it's because it's adulterated with rapeseed oil. But we can also see that in the oil that was new, we see no oxidation products, while in the old oxidized oil, well, in this case, it's simulated oil by heating it in open air, so it oxidizes faster. We'll see that the oxidation products suddenly show up. So by looking for these oxidation products, we'll see whether it's old or new. And here we talk about simultaneous investigation of quality and of authenticity. And to me, these two kinds of analysis is the same. I mean, if the manufacturer do the analysis to make sure that their product is okay and to document that it's what they tell it to be, it's quality assurance. But if someone else, the customer or representative of the customer, does the same analysis, it's basically to check whether the product is okay. So we are looking for authenticity, but it's basically the same analysis. What if we add different kinds of oil to the cheese? And if we look at the cheese mass spectra on the left side, we'll see the complete area. And again, like we did with the olive oil, we see mass spectra that looks almost the same. So how to detect whether there's a difference between them? If we look closer on the high area around mass 800, 900 area, we will actually see that there are differences. So when we add different kinds of oil like rapeseed, sunflower, soybean, we get mass spectra that looks different. But remember that this is ions that occur in low abundance compared to the primary components. And just like with the olive oil, this tells us that we are not looking for the distribution of the normal ions, we are looking for the distribution of some of the fingerprint ions of fatty acids or organic compounds that are not normally present in the milk that was used to manufacture the cheese. So again, fingerprint area, it's difficult to see the difference between these, so therefore we have to do it in a statistical way. A similar example, again, milk is to detect adulteration of goat or sheep milk. And goat or sheep milk is less abundant in the stores compared to cow milk. It's more expensive because it's more expensive to manufacture, and therefore it may be tempting to the manufacturers of goat or sheep milk to dilute it with cow milk. If we look at a PLS-DA model, which is partial to least squared discriminant analysis, this sounds very fancy, but it's just a different way of doing statistical analysis compared to the primary components analysis. But here we will see that the red and green dots are the goat and sheep milk, and they're very difficult to discern from each other. If we look at all the blue ones, it's cow milk. And looking at cow milk versus sheep or goat milk, that's very easy to see that they are different. The exciting part here is actually whether we can see if some part of the goat or sheep milk was substituted with cow milk. So we have plotted also some milk where 10% was replaced with cow milk, and some where 50% were plotted with cow milk, substituted with cow milk. And if you look at the black squares, you will see that it's very clear that they have moved halfway up towards the cow milk. So you can actually quite easily see the difference here. So even 10% cow milk is very easy to detect. Sorry. Yeah. It's actually 50%. Mass is just noticing that I'm saying the wrong thing. But if you substitute 50% of it, it's very easy to see the difference. Again, it's an example, and it tells us again that the fingerprint area may tell us a lot of stuff about the samples that the human mind cannot see because we have to look through hundreds, perhaps, of samples. But a statistical model will be able to see the difference here. A slight bit about the chicken feed. Again, it's a kind of quality control, and it was done by the European Commission. And if we look at chicken feed, we can it's customary to put in medicine to treat different kinds of parasitic or bacterial diseases. And in this example, it's been they have added two different medicinal products to the chicken feed, and they actually contain the same active component, which is diclasuril. I don't know how to pronounce it properly, and you can also see that the concentration is actually the same. But the cocciuril and the clinacox, which are more or less supposed to be the same, but it's two different products. I think they're from different manufacturers. If we look at the chicken feed, we can see that we get different mass spectra by using a polar solvent and a non-polar solvent. This is hexane in this case. And we can see that it's very important that we select the right solvent for the extraction, unless of course we do some kind of direct analysis. But when we've chosen the right solvent, it's just a matter of getting enough samples run. And if we look at this, we have run, well, the European Commission ran some samples of the two different medicinal products added to chicken feed. And they did it by running first a control group of each of them, and then an unknowns group, which is the same, but this is more or less a proof of concept method. So you can see that on the left side, the blue and black ones are the clinacox, where one of them is the black one is the control sample series, and the blue one is the unknowns, and it's very obvious that those are exactly the same. They're very easy to see that it's the same product that was added. If we look at the green squares, it's the control group for cocciuril, and the blue one is the unknowns analysis, the unknowns group. And the important part here is actually to see that we can see the difference between those two medicinal products. They're supposed to be the same, but apparently some of the other components in the medical product is different, so that we can see whether one or the other was used. You can also see in the right example where we have plotted the same analysis in positive mode, we get more or less the same results. It may seem that the distribution is more clear with the cocciuril control group, but apart from that, it's still very clear to see the difference. If we look at the data in the partial least squares model, then we also see that it's very clear that one of the products group below the line and the other product groups above the line. So again, it's very clear to discern the different products. And remember that this is chicken feed where only a small amount of the medical product was added. So again, it's fingerprint areas we're looking for, while the main components will be the chicken feed itself. So these are some different application examples of how you can see differences between products. You can see, look at the quality of the products. You can see some methods for discerning different varieties of products, and you can also see whether they were adulterated or not. So these are supposed to be some nice pictures that's up to you to decide. But it contains our telephone number, our email address for data inquiries. So I say thank you for your attention.